Hello again, and in practical part, I have also uploaded some tasks what we need to do today. We are going to equalize channel impulse response with minimum squared error equalizers. Yes, today we are going to look at linear equalizers. Next week we are going to look at non-linear equalizers, which perform even better than these equalizers, but they are, as you imagine, much harder, and we will consider Viterbi algorithm for that purpose. But that will be next week. And then you will also have quite big task for your, basically this is something like homework that we'll need to basically calculate and draw a picture of the receipt symbol, and that will be quite time consuming compared to maybe how much time we will spend for writing the code. Yes, but that will be next week. Today we are going to discuss simpler linear equalizers, most particularly minimum square equalizer and minimum square equalizer by using autocorrelation method and accordingly iteration method, which we mentioned in lecture. And basically we are going to do the same things as you already know. So we are going to display impulse response, amplitude frequency response of the equalizer of the entire system, QAM-16 constellation diagram, and output number of errors. Yes, for different number of equalizer orders. So basically what we are going to do is to start with the same simulation we go over and over again for quadrature amplitude modulation 16 without noise. So no noise in this practical exercise, and basically we need to display plots of channel impulse response and frequency response and QAM-16 signal constellation diagram for received signal in this channel. So each of you have the same impulse response as previously. Yes, in previous practical exercises there was same impulse response. I will use some more complicated impulse response, so we might as well start working. So I'm going to make, so we will have two methods. Yes, so I'm going to start a new file and call it EQ method 1. Accordingly, later I'm going to have EQ method 2. I'm going to okay, save. What's happening? Why not working? Okay, close, and then open it again. Some cloud issues. Sometimes MATLAB, I think MATLAB is okay, but Octave is like open source software. It might not work so well with clouds sometimes, but nothing terrible. Oh, I think I should restart Octave. Something is not looking good. So I'm going to go at once to that directory. Okay, I'm going to save in some other place, not in cloud. So this is some problem. So this is going to be EQ model 1. Some problem I don't want to spend time right now on trying to solve. Okay, as usual, I clear everything up, close all the possibly open plot windows, and let us start with task 1. Standing out comment like to easily notice where our task 1 starts. And here we basically, what was our first task? Generate QAM-16 signal without noise. Yes, so generate signal. So we have done so multiple times already, yes, to generate this signal. And today we are going to use again random integer numbers and address, well, basically array of pulse amplitude modulation values -3, -1, +1, +3, the same way as in the third practical exercise, I believe. Because here we don't need to calculate bit error rate, we don't need a specific gray mapping or stuff like that, so we might use simpler approach just to speed things up. Yes, because this particular practical exercise is dedicated to equalizers rather than a channel itself or a modulation. So we need to generate 10 power of 4 symbols. So let us specify these number at once. So this is number of transmitted symbols. Also, we need to specify impulse response. So we are going to use it. And I'm going to use longer impulse response than is specified for you, just to show you more, how to say, more difficult case for channels. So as you imagine, the more values we have in this impulse response, the more reflected stars we are experiencing, and the harder it is to design the equalizer. So we'll start with this impulse response and see how it goes. If I will need, I will make it simpler, yes, but for you, you only have 3 values here, each of you, yes, so you specify that impulse response which is provided to you. So this is channel impulse response. Also, it would be quite convenient at once to find the length of this impulse response. That would be h length of channel impulse response. Channel impulse response. Yeah. And now we can generate the quadrature amplitude 16 modulated signal as projections. Yes. So once again, I'd like to remind you that we basically have plus minus 3 plus minus 1 in both axes, and the result is formed as a complex number. Accordingly, we have real part, we have imaginary part. Yes, and we can basically generate any number in these values, yes, and accordingly make the complex number later on. So for example, we generate x as number one of these, -3, -1, +1, +3. We generate y in the same possible values, yes. And accordingly, then we calculate the complex point, for example, here as x plus y multiplied by complex I. Yes. So this same approach we are going to use. So let us specify first this QAM-16 signal generation. Okay. And let us specify first possible amplitude values, which are -3, -1, +1, and +3. So these are QAM4 values, yes, pulse amplitude modulation. And each of the axes, real axis and imaginary axis, has its own pulse amplitude modulation, which together make quadrature amplitude modulation 16. So let us then find the real part. So that would be real transmitted as random integers. So u, which is this array, yes, so consisting of 4 numbers, and then we are going to actually generate a simple random number from 1 to 4, Yes, and accordingly, randomly, we'll choose one of these four values, and we will repeat so for 10,000 times. So for that purpose, we are going to use rand E number generator. Well, rand E. Yes, and well, basically, we need to specify maximum value as 4 in this particular case. So rand E 4, and then we need to specify number of elements. That would be n by 1. That is random number generator. That would be a real part. Similarly, we now calculate imaginary part. Let us test if it's working as intended. Real part. I'm going to type unique real part and unique imaginary part. So there are only 4 unique values in each of them. So yes, we have these correctly. Now we can add together to form QAM-16 signal. And that is going to be our, so let us try and follow these same notations as here. Now this is a key signal. Actually, here is already some, example how to do the same thing. But this is for 4-PAM modulation. It's not quadrature amplitude modulation, yes, as in our case. Nonetheless, as I said, a quadrature amplitude modulation can be considered as 2 pulse amplitude modulations in rectangular signal axis, and so this works exactly the same. The only thing is that here it's proposed to use rand_int function. Let's check if it is available in Octave. Help rand_int not found. Package load communications. Maybe it is a part of this package. Yes, it's actually working exactly the same way as, not really exactly. First, so for rand E, you can see that first you specify range and then dimensions. Here, vice versa, dimensions and then the range. Yes, so the syntax is a little bit different, but other than that, they work exactly the same. So it's up to you whichever we'd like to use. So what I wanted to see is how we call this signal. So this is our original expected signal, which was from lecture, this AK. Yes, so in fact, we are going to call it AK then, and that would be a real transmitted part plus 1i multiplied with imaginary transmitted part. Original data. Now we can actually plot it. Yes. And also, yes, so we can actually plot it. Yes, that is the first. No, that is a task 1. We have done so. We have generated, but not yet transmitted. So now we need to perform transmission of this signal. And accordingly, for that, we are going to use the already familiar to you command called filter. So transmit data in channel will produce us, let's see this diagram schematic, will produce us with the signal RK. Yes, so basically that is our received signal. Yes, so going to be RK as a result of filter. Now, impulse response of the channel is H, and the denominator of this impulse response is 1, yes, because it's finite impulse response filter and it has no denominator. Now we are going to transmit our signal AK. Well, actually, considering that this filtering will ask L time intervals, we'd like to actually append some zeros at the end, and in particular, exactly L zeros. Yes, L minus 1, that is, because the sample itself is of the impulse response is our symbol, and then we have 4 extra symbols. Yes, 4 extra symbols in addition to our symbol. So that is L minus 1 zeros to be added in order to get all data. Then we need to cut out these first 4 symbols because they are incorrect. Only 5th symbol is correct. So that is how this filtering works. RK is going to be RK from L to end. That is because our filter has 4 delay units like this, yes? So it will, if our signal goes here at the time interval n equals 0, then here it will be at n equal 1, here it will be n equal 2, here it will be n equal 3, and at the output it will be at the n equal 4. Yes, so basically, if we start, so we can say that here is L minus 1, yes, and accordingly, considering that MATLAB starts numbering from 1 rather than 0, we have to add plus 1, and we get this L. And then we read all the remaining signals up to the end. So the first input value at the end of this filter, at the output of this filter, will be after these 4 time delay units. That is 4 in this particular case because here I have them 4. Yes, so we have to consider for that and understand that what are previous data, and at the same time this filter will produce some output. Only thing is that this output will not be correct output. It will be some initial data, yes, which needs to be removed. And for that reason, we remove first L minus 1 samples, yes, because of this filtering delay. This filtering delay always has to be considered in practical tasks, yes. So we have done so, and now we can get to the next display plot of channel impulse response and frequency response. Next task, yes, so that would be task 2. Yes, task 2. So we need to display plots. I can even copy this. I believe it should be fine. Yes, it is. So we already did so many times. So here I'm not going to be quite long in explaining. Yes, also I believe this also has some yes, impulse response system, frequency response is FreqZ. So yes, let us do the same way. The only thing is that we are going to have multiple figure plots, so let us make this as a figure 1. And here we are going to have 2 subplots, subplot 211, subplot 212. So for impulse response, in the same way, we are going to use stem, and starting from L to L minus 1. That would be our x-axis data. Y-axis data is going to be H, then red color, some formatting like line width, for example, 2.5, maybe. Read on. X label, so that would be sample number. Y label, that would be channel impulse response. And for this part, we are going to use FracUZ in the same way as here. The only thing I'm going to make slightly more different is to specify. Okay, something wrong here again. To specify this m value 256 as a separate variable, number of FracUZ samples. Yes, because I want to start plot from point 0 rather than 1. Automatically starts from 0. Also, yes, also you can see here it's 5, but most probably no. Here we have 8 samples, but okay, it's not important for us. Here they generated their impulse response of channel with a function fear1. Fear1 can be used to design a filter. Yes, instead of that, I have provided for each of you your own H values, which we will also use later on in next practical exercises as well to compare linear and nonlinear equalizers. So here we are going to use plot function because we want an uninterrupted line starting from 0 to m minus 1 divided by m. Yes. So that would be x data. Y data is going to be the same FracUZ h1m. Probably fine. Well, actually, we can make it also red color. I don't think we need line width here, but it's possible if you'd like. So grid on, X label, frequency. Well, normalized frequency, and Y label is going to be AFR, absolute frequency response. And actually, we need to plot an absolute value here, which is modulus. Yes. So here we have to plot abs for FracUZ and here. So let's check the brackets. So these are closed. So everything, here I haven't closed. Okay. Yes, you can see here they have plotted it in a separate way, just plotted FracUZ H1 256. Yes, it's like a separate figure. It, without using specific values, it produces the plot. So let's see how our program works. Maybe we would like to make it similar way. So yes, now it works. Yes, and you can clearly see here is our impulse response of the channel, and here is the amplitude frequency response. So starting from 0 and maximum up to 2. Yes, and it has some oscillation. So this is quite bad channel with fading at this frequency, and well, these basically are not really fading, but how to say it, above normal value of 1. So this will distort our data if we transmit signal in such channel. So that is our task 2, to display plots of these impulse response, of channel impulse response and channel frequency response. Okay, so now let's go to task 3. And task 3 is to actually simulate channel and display constellation. So transmit data and display QAM-16 constellation. So we have already transmitted data, yes, transmit data. Now we need to display this data. And accordingly, this is going to be our figure 2. Here we are going to have only one plot, which is going to be plot real part of RK, imaginary part of RK, and these are going to be blue stars. Yes, for example, see them clearly. Also, we want to plot unique values. So that would be U and U. Yes. No, that would be not really enough. We need to plot real unique RK and imaginary unique RK. And these are going to be red cross, not crosses, but circles. And let's make it also line width 2. We need grid lines. We need square axis square, to have the same dimensions on both axes, on X and Y. Also, I think we might as well add this line width here too. Okay. And labels. X label is real part. And Y label is imaginary part. So that's going to be the constellation of received and ideal signals. Let's see how it will look like. Sorry, not RK, but AK here. Our original signal without channel effect. Yes, here you can see our received signal, and well, basically you can clearly see that it's scattered around and probably it has some errors. Now what we need to do is to actually evaluate the number of errors without noise for channel, without this equalizer. That means that we again have to demodulate this signal. This time, however, we are going to make some simple and fast demodulator. So that is going to be task 4. Task 4. Modulate data and plot, not plot, but output number of errors. That's what we are going to do here. For that reason, we need to make the demodulator. So let's make this demodulator first here in how to say it, in the code, and then we are going to format it as a separate function in a separate file so that we can easily call it with a single line. So the idea here, how it will operate, let me actually show you it again, is that as you can clearly see, we have these values scattered much further than plus minus 3, and so forth. So what I'm going to do is to consider that everything that is more than plus 3 or less than minus 3 is actually plus 3 and minus 3. Yes, so I'm going to truncate it. Yes, so basically I say that here I have the square box, and all the points outside of the square box are considered to be belonging to this line of the square box. So now I'm going to make that, and also I'm going to display you how it will look like. Okay, I'm sorry for a minute. Okay, let's continue. And yes, so real part of uh, real part of these symbols after equalizer. But actually we haven't had this equalizer yet, so no. So for now it's still real part of this RK. So let's call this RK, real part of RK is going to be real. But then again, considering that we will have equalizer, and equalizer has to be done before demodulation and detection. So we can say that this is actually going to be QK. Yes, so that is going to be, and for now we say that we have no equalizer. So QK is exactly equal with RK. So no equalizer used. Sorry, where I have written it, it should be in the end here. This should be also. So that is going to be QK. Real part, yes. And accordingly, yes. And accordingly, we need also imaginary part, which is going to be image. Okay. Here, I believe this decoding is also present. Or no? No, not really present. It's one of the tasks, I believe, yes. But okay, let's see then further. Now what we need to do is, as I said, limit all the values by plus or minus 3. So all the QK values that are below minus 3 should be set to minus 3. All the values that are above plus 3 should be set to plus 3. Yes, well, I'm not writing this plus. And similarly for imaginary part. So now all the values will be in this box between minus 3 and plus 3, because they exceed it anyway, and during the detection they still will be considered sorry, I wanted to change this to image. They still will be considered as plus or minus 3. It doesn't really matter for that reason. Yes, so now let's update this plot and see how it will look like. Real QK, image QK. Blue stars. Axis square, of course. Axis. And here Yes, and here I do need to change to imaginary as well. So now, as you can see, all these points that were previously outside now are concentrated here, because it doesn't really matter if the point is here or it is here, it's still going to be closest to this point. Yes. And it will regardless be evaluated as one of these points. So what we want to do next is to actually demodulate it. However, thanks to this fact that now we have these numbers in this range, we can simply round them out. Yes, so here I'm going to offer you this simplified detector, which operates very fast and doesn't produce much memory. And basically we can detect QAM-16 symbols by rounding. Oh, I have closed that plot. Yes. Let me actually display it once again. So that is going to be plot real QK, imaginary QK, axis square, and grid. Oh, sorry, I needed dots. Not really dots, but stars. So I can mark here my original points. So that's going to be this point, this point, this. Well, actually, it's faster and easier, I believe, to copy that code. Like this. Line width. Probably rounds will be better. Yes, so what we are now going to do is to actually simply consider it in two projections. So for example, consider this point. Well, let me choose another color. Consider this point, for example. What we are now going to do is to separately find the closest vertical projection and the closest horizontal projection. And this is achieved by simply rounding the symbols. Similarly, this point will go to this point and this point, right? So in general, the closest one will be here. And again, this is simply rounding. So, however, it would work as a simple rounding if we had here like 1, 2, 3, and 4. So anything that is between, for example, 3.5 goes to here. Anything that is below goes to here. However, we have here step of 2. But this is nothing very difficult. We can convert numbers mathematically so that 3 becomes minus 3 becomes 0 and plus 3 becomes 3. So let's make this conversion. So that is going to be, for example, yk as a real part plus 3 divided by 2 and the imaginary part this. Yes, so now I'm going to plot the same again. The only thing is here I'm going to real yk imaginary. So as you can see now, we are concentrated in this square. Here we have 0, here we have 1, 2, 3. and similarly 1, 2, 3. So any number now. And accordingly here we had our crosses as well. So we can now simply round off each horizontal and vertical projection, and basically we will end up in this point. So let's do that and add this rounding. So round. The only thing is that we need these brackets. So we want to round the entire thing, not just this real part. And now it's again going to be integer number 0, 1, 2, or 3. In order to convert them back into these numbers, yes, we can basically reverse what we have done here. So multiply with 2 and subtract 3. Yes, so multiply with 2, subtract 3, subtract 3. Now we will have them concentrated in this particular point. So there are many points. So what we want to do now is to check out, are they really correctly received or there are any mismatches? So that's exactly what I was showing you in this lecture here. Yes, so we can actually display similar thing. So considering that we have no equalizer used, we don't even need to worry about any delay. So let's see. And finally, we need to have this find detected, not really find, but specify detected. What we are going to do now is to compare these what we have obtained after rounding as a detected signal with the original signal AK that was here. They should match because we don't have any noise, but we have unfortunately very bad channel, which basically most probably has been a source of severe distortion in our data. Yes, so let's see how bad is this situation. So now I have specified this, and we can actually so YK, it's in a row. I want it to be as a column, and I want the first 100 values. So that is our received data and our original data. So let us compare it one by one, simply specifying them as this array, yes, to be outputted. And we can clearly see that sadly they don't match. Yes, these are different, these are different, these are different, different. Not one of them so far matches. Yes, and this isn't the problem of modulation, because if we well, we don't have any noise here. So let me make simpler channel H1 and 0.1, which shouldn't make so much problems to our signal. Yes, so if we will have that's interesting, but okay. If we will have the same situation here again, then that means we have some problem with detection. But you can see clearly here that now at least some of them are now matching. Yes, here we have match, here we have match. Sure, we have also here a match. Yes, so basically it's no longer so bad. At least sometimes we now receive correctly, even with this channel. Yes, well, if we make it like this, then obviously, we shouldn't experience any difficulties, yes? But still, wait a minute, I understand now. This part and this part are the same. So for some reason, this first value is lost. Yes, so that means, that means that somewhere here, when we were reading our data and appending zeros, we have lost too much. Yes, so let me actually double check if I am correct here. So L minus 1, L. Yes, we had to actually start from L plus 1 here and add L zeros. I believe it's so. Let's check it again. No. Now we have 2. Yes. So basically, it's probably meaning that we had L minus 1 here, and we should also have L minus 1 here. Oh yes, time delay is something to be considered. Yes, now you can see that they match. Yes, so that was because of incorrect time delay. So now if I return my impulse response, once again, you will see that there will be some problems with detection. Even so, we have a lot of errors. Yes, sometimes, most probably, it will match, but it's very difficult to find manually. So instead, let us just assign this task to computer and calculate all the number of, how to say it, mismatching symbols. So what we need to do is to compare A symbols, original symbols, and check which of them are not same as Y symbols, and add them up together. However, now I want to double check how many we have these symbols and how many we have these symbols. So we have one extra symbol here, which is odd. So that probably means we need to subtract 2 from here for them to be of the same length. Yes, now they are the same length, 10,000 here and 10,000 here. Now, we think, I understand now, so number of these symbols is L minus 1. So we have to take this number of these symbols minus 1. So that is L minus 2 in total. Yes, so now everything is fine. And we accordingly can see the number of errors here is 9,000. 9,000 out of 10,000. Yes, so there is almost 1,000 of correctly received symbols only. That is 10%. Just 10% have been sent correctly. Well, unfortunately, that's how it's working. Yes, so we can add some message fprintf number of errors. Yes. So no equalizer. And then output the results. Okay. Now what we want to do is to apply equalizer and see if things improve. However, before we do that, I'm going to save this as a new file. make this a function. Going to be function. So the result is yk. The function name is going to be detect QAM-16, and the input is going to be qk. Now everything will be shifted here. I'm going to save it with the file name detect QAM-16, so the same as the name of the function. Yes. And here, accordingly, I'm going to replace this line with the yk equal to detect QAM-16, and this is going to be qk, like this, right? Okay, it's working. Now, if we use this more simple impulse response, then the number of errors is going to be 0. It's 0 because this inter-symbol interference is just not enough to make incorrect decisions here, right? You can, even with your own eyes, clearly see that all these points converge to this center. Yes, so no problems here. Now, that was task 4 without equalizers. Now what we want to do is to start working on our equalizers. Yes, and first of all, we are going to use autocorrelation method. Well, of course, first of all, we need to calculate this equalizer. That is the task 5. Then, for that equalizer to plot some results, then demodulate signal and accordingly output the number of errors, which is, well, basically the same thing. Okay, so that's our task 5. Calculate equalizer and display results. So for this, we are going to use autocorrelation method. So I'm going to specify this as autocorrelation method. Similarly, then I'm going to save a copy of this file, and this is going to be equi-model2, where I'm going to make the equalizer with the iterations method by modifying this file. So first of all, I need to specify the number of equalizer order. Yes, so that is 15, 31, and 45. So L equalizer is going to be starting with 15, the smaller number. Yes. During the calculations, we are going to rely on the central value of this equalizer impulse response. So total, we have L equalizer, but we also need to know the number of this central one. So that is going to be L equalizer minus 1 divided by 2. So, well, it's not really this number. This is rather like this number, yes, before this. So that is going to be, if we have here 15, then this central position will be at 8. Here we have 7. Yes, and here we have also 7. So 7, 1, and 7. That gives in total 15 positions. Yes. So I'm going to call this variable as a half, like you half. So L equalizer minus 1 divided by 2. Impulse response length and half of it. Now let us specify these variables. So what we need? We need autocorrelation matrix for real part, real phi1, imaginary phi. We also need a real alpha and imaginary alpha, right? So we assume them to be equal to zeros initially. So initialize correlation matrix and vectors. So first of all, autocorrelation. So that's going to be real phi zeros, and this is the any autocorrelation matrix is a square matrix. So basically, we can even Wikipedia it right now. Yes, autocorrelation matrix is a square matrix. Yes, with the same dimensions n by n. So here you can see average value of x11, average value x1, x2, and so forth. Yes, accordingly, we need to calculate all these average values for each row and for each column positions. So we will do that by using the existing code provided by that material I have offered you. But initially, we need to specify here that it is zeros matrix with dimensions of impulse response length of our equalizer. So that's auto correlation matrix real part. Similarly, we are going to calculate imaginary and also we need cross correlation vectors. That would be real alpha, imaginary alpha. So zeros, but this is a vector, so the second dimension is just 1. Okay, now let us set also comment that this is cross correlation vector, real part, cross correlation vector, imaginary part. So that is some preparation. Yes, we have prepared empty matrices and the vectors that we are going to calculate now. Also, we might need a real part and imaginary part of our received signal. So here, this is our received signal we are going to use as an input for equalizer. Yes, so separate real imaginary part of signal. So we are going to have RK real, RK imaginary. Real. Accordingly, RK real will be used to calculate real phi autocorrelation matrix and real alpha cross correlation vector, and similarly, imaginary phi autocorrelation matrix and imaginary alpha cross correlation vector will be used to calculate from this imaginary part, right? So now we need to calculate this matrix. So actually, for that, we can copy this part of the code and basically update it. Yes. So copy and calculate auto correlation and cross correlation matrices vectors. One thing is need to delete all these. Now we need to replace. Here we are going to have, so in our particular case, L equal. So let's see how much is here. Equalizer. Equalizer is 31. Yes, so this is L equal half plus 1. So this is L equal half plus 1. This is accordingly L equal half. Next, this is our RK, which is complex number. Again, here as LEQ half, LEQ half, right? So this is some raw correlation matrix. Now, this is our autocorrelation matrix. Well, okay, let us make this real part. So this is real. Accordingly, this is going to be a real phi as a real phi. Here you can see that we add, yes. And accordingly, alpha, alpha. So that is going to be real alpha and real alpha. Here we are having a real part. So that is real tx multiplied with Rx real. So rather complicated, but let's now try and check this step by step how this operates, right? Also, I need to replace this part. Minus L minus 1. This part. L minus 1. Well, I'm not really sure about these. Do we need them? But for now, I'm going to comment them. So I'm going to put a breakpoint here so that once my software code goes up to this point, it will stop and allow me take step by step to see what is happening inside this for loop. So let's see it. So now we have stopped at this position and we can see how does our autocorrelation matrix, for example, real part, look like at the specific moment. Real phi, it's empty, it's zeros matrix. Yes, real phi, 15 by 15 matrix. So what we are going to do now is to take this part of the, let's say it, our data, this real data, yes. So actually, let me display RK real first 100 values, and I want to do so in column. Yes, here they are. So what we are going to do now is we are going to split first 15 values. So basically, we are going to cut them out, and that's exactly this part. Yes, so we start with I equal to minimum value of this. So if we subtract from LEQ half plus 1 just LEQ half, we are left with simply 1 and go up to LEQ half plus this value, that would be double LEQ half. All this is simply LEQ. Yes, so first this will be from value 1 to value 15. So let's see if it's true. Also, I need transpose, yes, and you can clearly see that indeed these are first 15 values. So what we are doing that next is flip them. Yes, so this is going to be first, this is going to be last. So that is done with using flip upside down function. Flip upside down. now we have flipped it, and what we are doing with that is that this is going to be our basically this variable. Now, what we make from this is a autocorrelation matrix. So basically, we multiply this position, the number with itself. For this position, we multiply the number. Well, basically, it's simpler maybe to write. So basically, first is going to be minus 174 squared. Here, we are going to multiply minus 1.74 with 0.54. And here the same value, 0.54. Here we are going to have 0.54 squared, and so forth. So basically, autocorrelation matrix is quite simple. Yes, diagonal will contain squared values, and any other accordingly is going to be 1.74 multiplied with the third value, minus 2.78. And here, accordingly, we are going to multiply minus 1.74 with minus 2.78, and so forth. So for this, we are going to multiply minus 2.74 with the 0.54. Here we are going to multiply, so the second row, 0.54 with the third, minus 2.748, and so forth. So you can see here that for this entire column, the second multiplier is this number, and the first multiplier is this entire column. So you take this entire column and multiply it with this number, for example, first number, and you have your first column. You take this column, multiply with the second number, you have second column, and so forth. Yes, so that's how this matrix is formed. Yes, so let's see how does it work. This is actually achieved by calculating this. It's not yet calculated, so I need to take a step. Not next breakpoint, but just a step. Yes, so now I have this value, RK real. Yes, and now I can calculate this. So this is our autocorrelation matrix, yes, which is symmetric, meaning that this value, wait a minute, so this is, yes, this value and this value, this value, and this value, this and these are the same, and accordingly here it goes like this. Yes, so this is autocorrelation matrix, which is then added up. Yes, previously it was 0 in the first iteration, but it will accordingly with each next 15 symbols update itself. Yes, so basically what is going to happen now is that we will at the next step take not really first 15 symbols, but starting from the next, these 15 symbols, recalculate the same autocorrelation matrix, add it on top, add it on top, add it on top, and go through all our data in this small sliding window. Yes, and basically update our autocorrelation matrix with each iteration. So that's how we calculate this total autocorrelation matrix. Now for the cross correlation matrix. Yes, here you can see that, for example, in this particular time moment, our value I is 8. So we are interested to see what was 8 value. It was 1 real value, that is, yes, before channel. Now what we are going to do is to actually multiply it with any other values we have. So rel tx multiplied with all the possible received 15 values, yes. rk real. And accordingly, well, since it was 1, nothing really changed. And that is our cross-correlation vector. And, well, 1, 2, 3, 4, 5, 6, 7, 8, 8 is here, yes, in the middle, and all the others are like, this is our position of our real symbol, that should be. And as you can see, it's not really the biggest possible value in this particular case. But it's okay, it will be considered in average, yes, so we need to calculate now the average. So in order to calculate average, that means that we need to calculate autocorrelation function for each step, then add them up all together, and then divide with the number of these autocorrelation functions. So that's exactly what's happening here, yes. So here in this for loop, we calculate many of these autocorrelation functions, yes, add them up together. Here you can see as they grow up. The same goes for the vector, and here you can see that we divide them with the amount. So that gives us the average, yes. So I'm going to stop this now, remove the breakpoint, and let's calculate the entire thing. So now we have this autocorrelation matrix. We have this average cross-correlation vector, yes, which we can use to calculate our filter coefficients, right? So let me actually double check if it is correct here. Okay. But wait a minute, was that L or? Yes, this is L minus 1. This is L minus 1. For some reason here I have it. Well, okay, we'll get to this later, but for now we need to do the same thing for imaginary part as well. So this is a cross correlation vector update. And this is not update, this is just the vector of received signal of length L equal divided by half. So here we normalize to find average autocorrelation and cross correlation. At any rate, this procedure calculates these autocorrelation matrix and cross-correlation vectors that we need to find the filter coefficients. Now, we do the same thing for imaginary part. So that would be RK imaginary. Well, basically, I believe I can copy-paste this. Say that this is real part. And this is going to be imaginary part. Imaginary. Also imaginary. Okay. So I hope I haven't missed any of them. And similarly, now we need to normalize for imaginary as well. And here the length is the same. Okay, so normalization is complete, and now we have our correlation and cross-correlation vectors. Now, what we need to do further is to find our equalizer. Here is the solution. We need inverse matrix of the autocorrelation matrix and multiply it with cross-correlation vector. The result will be our filter that we need to actually equalize our data. And then we will be able to test how it works. So now we can say calculate equalizer coefficients. So here in their uh, material, they have notated it as C. However, in our lectures, it was notated as HEQ, so I'm going to use how I was showing you in lectures, yes. And furthermore, you need to consider that we are going to have a real part and imaginary part. Or rather than that, H real EQ, imaginary EQ. So we do so in accordance with the formula. Inverse of the matrix. Now, the good thing for autocorrelation matrix that it is always it always has inverse matrix. Yes, there is no case that it cannot exist. So for autocorrelation matrix, there is always inverse matrix. So we don't even worry if there is or there is no such matrix. That's not a concern for us here. So real phi with real alpha. Same goes for the imaginary part, inverse matrix of imaginary phi with imaginary alpha. So we have calculated these two equalizers, one for real part and another for the imaginary part. What is now left is to actually plot this equalizer, impulse response and frequency response. Yes. So let's see how these equalizer coefficients look like. So that would be H real EQ and H imag EQ. They are a little different, right? But still somewhat similar. But let's plot them, because this way it's quite difficult to tell. So plot the results. And accordingly, that is going to be our figure number 3, right? Now, we are going to need 4 subplots. Subplot 2 to 1, plot 2 to 2, 3, and subplot 2 to 4. Now, for the impulse response, we are going to use stem. For the frequency response, we are going to use plot. And in fact, we already displayed the similar plots for channel. Yes, so I'm going to copy this entire line and replace it here with LEQ. Here, accordingly, H real EQ, H imaginary EQ. So that would be real or imaginary equalizer impulse response. That is going to be real equalizer. Now, similarly for frequency response, yes. So I'm replacing this and this. Freq Z here, H imaginary, EQ, each real EQ. And accordingly, real equalizer, here imaginary equalizer. So now I'm going to copy this piece of code just to make it faster. So you can see that we have calculated this equalizer that is intended to compensate the impulse response of the channel. So let's make this code. And then we will calculate the entire system, both transmitter and receiver, impulse response. So if we compare this frequency response, these and these, you can clearly see that where this is small, this is big, and vice versa. This is small here, and this is big here. So they match and compensate each other so that they roughly will be around 1. So let's see now how close we were to this and how will impulse response look like in this particular case. So plot the results for equalizers. Then accordingly plot the results for entire system. Basically, as you already have seen, these plots look very similar for real part and imaginary part. So now I'm going to plot just one of them, just real part. Yes. So that is going to be figure 4. Accordingly, I will need these two plots. But before that, I still need to calculate that entire, how to say it, or rather than that, I can actually make it in, well, no, I will make it this. So the entire system impulse response is going to be H system convolution between channel impulse response and equalizer impulse response. Example, real part, yes? And then we can actually plot it. So I'm going to replace it here and here. System impulse response and system amplitude frequency response. So once again, I prefer to try and run this in a faster way. And something is missing. Okay, let me just try and run it. Figure 3, figure 4. Ah, wait a minute, I need it to 1 and 2, 1, 2. Some error. Wait a minute, what happened? 92. Ah, wait a minute. Here we will have now total length much more, which is H system 19. Yes, so basically it's longer by L, where L is L minus 1, where L is minus 1, so okay. Plus L minus 2, yes. Wait a minute, where is the second plot? Okay, now it's working. Yes, you can clearly see that here in the center we have 0, not 0, 1, and here we have something very close to zeros. Yes, here you can clearly see that it's not entirely 0, but anyway, it's close. Also, our amplitude frequency response, actually, let me force it to be plotted from y limits from 0 to 1.5, because this way it's looking not so nice. It should be more, how to say it, more linear. Yes. Now you can clearly see that it's become better. So the amplitude frequency response of our channel was like this, and the amplitude frequency response of our channel and equalizer is roughly this. So ideally, we wanted to receive the line that goes here. Obviously, we couldn't do so. And the last question that remains is how many errors there will be now after equalizing. So the last point is count number of errors. Not really. Last point. We need to plot QAM-16 signals. Yes. Accordingly, yes, I can see that we are close to the end of the time, so let us finish this part, and the second part will start next week. Because we have 3 lectures, we will be able to do everything in time. So let us now perform this equalization. So first of all, we need to perform equalizer of signal of receipt. Because we have calculated the equalizer itself, but we haven't applied this equalizer yet. So equalize of received signal. Equalize just received signal, right? So again, we are going to use filter command for this purpose. That would be real part QK equal to filter. Here now we use H real EQ one, and here we are going to use as the input RK real appended with zeros 1 LEQ half. Yes, as I said earlier, we need to start reading our data starting from the middle point of our equalizer. Yes, that where we have that maximum value of 1. This is right in the middle. And accordingly, all the brackets have been closed. Similarly, we work with imaginary part. H imaginary, like this. Now we need to reconstruct QAM-16 signal before detection. And then, accordingly, detect that signal, right? So that would be QK. Now, as you have seen here, we didn't really perform equalizing here, so here we skip that part. But now we are going to basically do the same stuff as previously. So that is going to be real QK plus imaginary QK multiplied by complex 1. Also, we need to cut off the first part, yes, of the signals and start reading our signal from this value. So QK LEQ half plus 1 up to the end. That is going to be our new QK value. So we truncate those first half of the impulse response values, which are anyway incorrect, because for this time filter is only starting to work and it doesn't produce any output. The first output will be produced at this time moment, LEQ half plus 1, once we have passed the first half of the impulse response. And then all our data will go through. So now we can plot this constellation. So let me copy again. That will be part. The only thing is that I want to use figure 5. And here I'm going to plot QK. This is fine with ideal signal. So currently we still haven't performed detection because we want to see how it will look like before detecting. So let's see. And error. So problem is with this command filter. Filter. So that is before equalizing, that is after equalizing. It's obviously became better, but what's about correct reading? How many errors do we have? For that, we actually need to perform detection. But however, since now we have this function ready, so where was that? We can simply copy this part, and that is going to be it. Yes, only thing I'm going to say that here I use MSE equalizer and equal to like this. Yes. So let's see how many errors will be now. After equalizing, we have only 9 errors left. Yes, out of 10,000 symbols. Obviously, if we increase this equalizer length, the length of the impulse response, we should expect even better results. So let's see what tasks there were. 15, 31, and 45. So let's try 31 and 45. So that would be LEQ at the beginning. Yes? No. Here. And let's see the plots. Only 4 errors, and also this response is much more smooth. We expect to have a straight line, and we almost got it, as you can see here. And here also the deviations are much smaller. And for 45, this is expected to be even better. Yes, so 45. Now, for the number of errors, I'm pretty sure that we should get 0. Now, I'm not really certain where I have mistaken now, but somewhere there is my mistake that produces this extra 2 errors. Here you can see almost straight line. This equalizer is almost perfect for this channel, yes? So we have now knowledge how to calculate this equalizer. And well, next week we'll start with the second part of this practical exercise with the iteration method, which will calculate exactly the same equalizers. Yes, exactly the same equalizers with a different method. And we'll see what is the k-value, the specifics of that method. Here we had to calculate this autocorrelation matrix, which is quite a calculation intensive process. And also we needed to find inverse matrix, which is also quite complicated operation. Yes. But iterative method is more, how to say, easy computations friendly for simpler processors and simpler software code. Okay, are there any questions for today from you? So if no questions, I'm sorry again for so longer today. Hopefully you'll be fine and get to next lesson time. And thank you and see you next week. Next week we also start at 9 and we'll continue. Thank you and goodbye.
Thank you, Professor.